Are there any questions on homework? No. All right. I'm going to maintain a list here. Over the next few class periods, we're going to learn lots of ways to determine the behavior of a series. And as we learn new ways, we'll add it to the list. Right now, it's not a very long list. But we're able to get some progress, and that is we're able to analyze the sequence of partial sums. We did it for geometric. We could find a formula for S, and then we could take the limit. We did it for one other example where, remember, we could make the terms in Sn telescope away, and then only two terms were left. We could analyze it. Your homework has, I think, two different problems where you can do the very same thing. In fact, that's how you do it. However, we've pretty much done what we can do here. And with the exception that there probably, well, I think I can say there will definitely be a question on the next exam about the sequence of partial sums. So I'm going to let you give you the chance to show me that you know what's going on. The second thing is, like I said before, geometric series. We can analyze them 100% of the time. And when they converge, we can find the value they converge to, okay? And I posted, or in class, we've done 3 different sort of physical problems where geometric series are how we solve the problems. So, we recognize how to spot them, got to learn how to do that. But once we figured that out, they're easy to work with. 100% of the time, we know whether they converge or diverge. When they converge, we know the values. All right, today we're going to add a couple more. I'll set the list up now. I'm going to talk about something called the divergence test and something called the integral test. And as a consequence of the integral test, we'll identify a particular category. It's called the P-series, and I'm going to call it a test. The textbook might not. But the test is something we can run to determine the behavior. Why do we need a whole bunch of them? Well, you never know which one is going to work. If the series is not a geometric series, then the second one's not going to help us one bit. Right? And you'll see. And we're going to add a lot of tests to the list before we're done. Maybe 5 more. At least 4 I can think of off the top. No, 5. Yeah. So the next few class periods will come. Maybe I'll quickly reproduce the list we have so far, and then we'll make space for the new ones. All right. No questions on the homework. I said on Wednesday, maybe I didn't. Maybe I said it this morning at 9. I'll say it again at the risk of saying it twice. For a while, our focus is on determining if the series CR converges or diverges. converges. We are not concerned for a while. And we'll come back to it later. About the value. Does it converge to 5 or 12 or 17? And the reason we're not going to care about it is because these tests aren't going to tell us what we pick the right test, and it will tell us converges or if it diverges. But tests don't have the power to tell us the value it converges to. So we're going to give up on that while we learn all about all the tests. And like I said, later on, we'll come back to the issue of what do converging series converge to. All right, like I said, the first test I'm going to talk about is the divergence test. So I have a series, an infinite series. And I'm not going to write the index. I don't really care if it starts at 1 or 5 or 13. It's going to go to infinity. Of course, everything we talk about here, every sum. And if we talk about a sum that's not an infinite sum, then I'll write the indices information so that we're clear. I want to determine behavior. If the limit as n goes to infinity of a sub n is not 0, it diverges. It's that easy. As suggested by the name, this test can only tell us when the series diverges. On the next exam, I typically give students several series to look at and ask them to determine the behavior and identify the test you're going to use. And every once in a while, I'll have a student say, this series converges by the divergence test. Well, that's impossible. It's a well-chosen name. It wasn't invented by a guy whose last name was Divergence. It was named because of what it can do for us. Okay, and of course, it doesn't work all the time. If the terms of the series go to 0, this test is worthless. Doesn't help us. We can mark it off the list like, okay, not going to help. Think about on Wednesday, we analyzed the harmonic series. What did we decide about it? We figure out if it's divergent or converged. Pardon? It diverged, yeah. Yeah. The limit as n goes to infinity, 1 over n. What is it? 0. If the terms go to 0, this test will not help us. And we don't know what's going on. We have to invoke another test. If the terms don't go to 0, it diverges and we're done. Okay? And it doesn't matter if the limit exists or not. If the limit is not 0 because it doesn't exist, well, that's not 0. It diverges. If the limit is 0.0001, that's not 0. It diverges. Pretty simple test. You know, way back in chapter 2 of Calc 1, we learned about limits, and it's like we just keep coming back to them. So, you know, in theory, we're experts. We've been doing a lot. Not only did we do them in chapter 2, we've seen them since. We learned something L'Hopital's rule. Maybe it could come in here. All right. Summation n over 1,000 plus 14. N goes from 1 to infinity. Converge or diverge, what do you think? Well, let's think about this. I have a list. We can't go below 3 because we haven't talked about these yet. Do we want to analyze the sequence of partial sums? Yes or no? Ken? Yeah, I see you were moving your head the right direction. Yeah, I mean, it's rare. We're never going to pick. In fact, what we're going to learn is like to go through these series of tests. And while this is the very first one we learned, it's not really a test. It's the mechanism for deciding. We're actually going to think of like moving it way down to the bottom. Like we're going to go through all the others before we start to think maybe that's going to work. Noah.
So with the divergence test, is the limit does not equal 0, but that does equal to 0 in divergence?
If the limit is not 0 of the terms, we're ignoring the sum, we're looking at the formula that generates the terms. If that limit is not 0, the divergence. All right, so the one I wrote, is it a geometric series? No, how do you know? There is no exponent, absolutely. Therefore, if it's a good problem for us, maybe I'm careless here and I've asked a problem we're not ready for, but the divergence is really the only other one. We haven't talked about those, so let's take a look. We need to know what is the limit as n goes to infinity of n over 1,000 n plus 14. What do you think? Anybody know? 1? I'll go with that partly, but I'm not done. 1 over, no? 1 over 1,000. Polynomial divided by polynomial at infinity, the degrees tell us what's going on when they're the same. The limit is the ratio of leading coefficients, 1 over 1,000. Is that 0? It's not 0. Therefore, this series close to 0, close doesn't count. If it is not 0, series not. Okay. Pretty easy test to use. Assuming we're up to speed with our limits. On the online homework for today, due Monday, the section we're in, I think it's section 3, is entitled Divergence Test and the Integral Test. So both of them identified in the title. When I go to look at the problems that are implemented in the online system, there is not a single one where the divergence test resolves the issue for us. And I don't know why that is. So I posted a picture of some problems from a book that I used to use. And so be sure you find it. I'm going to ask you about it on the next quiz, next test. I mean, it's entirely possible that you will have to use the divergence test on the next test. Unfortunately, I can't point you to online homework problems, but I can post problems. And really, as a student, you ought to pay closer attention to the ones I go out of my way to post for you, right? I'm your teacher, not XYZ. I decide what grade you're going to get in the end. So if I go to the trouble of posting something extra above and beyond, then you got to take careful attention to it. All right, the integral test. I don't know if you've noticed lately, I've gone to always keeping the calendar at the top of the website. And so you should always, every day, you should scan the things I've added in below the calendar. Make sure you're seeing them. And some of them are problems for you to practice on. Some of them are solutions to those problems that I've posted. Noah.
I'm still kind of confused on the 1 over n. It diverges to infinity, right?
The series does.
But
So, okay, so the lesson here is if the limit is 0, the divergence test fails. It doesn't resolve the issue for us. Because here is a series. We know it diverges Yeah, the terms go to zero. If the terms go to zero, we have not decided anything yet. We're going to go to our list and find another test to run. If the limit is not zero, we're done. It diverges. Okay? So some divergent series, the limits go to zero. So the divergence test doesn't work in that case. Okay? The integral test. So given an infinite series, identify the function. That is, a sub n is just another way to write a function. And I'm going to talk about an integral. So I want to convert it to the notation that we use for integration. So instead of calling the function a sub n, a of n, we'll call it f of n. I think when we started sequences, I used this one. If, number one, f of x is bigger than 0 and continuous, decreasing, f of x decreasing, three, f of x, let me write it formally, the limit as x goes to infinity, f of x equals 0. If those three things are true, then the integral, from wherever we start, I'll use one, doesn't really matter, f of x dx. The improper integral of this function from some starting point to infinity and the series that we started with have the same behavior. Behave the same. Remember, for improper integrals, we use the same sort of language, converge, diverge. And presumably we're experts on improper integrals because that was last chapter, right? And I've given you a test over it. And so the idea is that we can take the series whose behavior we don't know, take a look at the improper integral whose behavior we may not know by looking at it, but we know how to work it out. And then we can infer the behavior, however it turns out, to the series. All right, I want to show you why this is true. It's kind of like a proof for it. Let's start with, let's say, suppose the integral from 1 to infinity, f of x dx, it diverges. It equals infinity. If it meets these conditions, then the only way it can diverge is by going to infinity. Because it meets those conditions, I can draw a graph. Yep. I don't know what it does over here, but starting at 1, it's got to decrease to 0. All right, I want to fit some rectangles to this graph, and I want to do it like this. Take 1, run him up, come over, and then 2, 4, and so on and on and on, for every integer. How much area is in the first rectangle? How tall is it? F of 1, is that what you said? Can we call that a sub 1? Yeah, and how wide is it? 1. So the area of the first rectangle is the first term of the series. A times width, A1 times 1. How much area is in the second one? A2 and A3. Is there more area in those rectangles combined or under the curve? In the rectangles, yeah, they all have a little bit of slope over the top of the curve. All of them do, because the function is decreasing. So if I add up all the rectangles, I'm going to get a number that's bigger than the area under the function, which is this. But how big is it? Goes to infinity. So the summation, a sub n equals 1 to infinity, is bigger than the integral from 1 to infinity. F of x, f and a, so of course, connected. That's infinity. So this guy has to diverge as well. So the integral diverging means the series. All right. Suppose the integral converges. So our picture, it's about the same. And then here's 1, 2, 3. Yeah, what I'm going to do is form rectangles underneath the function. How much area in this first rectangle? How tall is it? F of 2, how wide is it? 1. So the area in the first one is a sub 2. And the next one? I said it, I didn't write it. We're now looking at the case where the integral converges. If I add up all those rectangles, do I get more or less than the area under the function? I get less. Yeah, I'm missing. Instead of pieces flopping over the curve, I'm missing some area. And therefore, the summation n equals 1 to infinity. A sub, oh, starting at 2. That was the first one. Is less than, is strictly less than the integral from 1 to infinity f of x dx, which by our assumption is finite. Therefore, if I ignore the first term of the series, right, to fit all the rectangles under the curve, I really couldn't have one whose height was a1. So we ignore it. We analyze all the rest of them, a2 off to infinity. Those add up to a finite number, less than this integral. And now what happens when I add a1 back in to get the originals? Is that going to like blow it up and now it's going to diverge? No, it's going to be whatever value it is now, less than the integral plus the first term of the series, whatever that is. It's a finite value. Now, it may make it bigger than the integral, but you can't make this thing infinite by adding a finite number to it. So therefore, if I add all the terms in 1 to infinity, it's going to converge. And that's the justification for the integral test. In the converging case, we really can't make any conclusion about the value of the series. There really is no relation, no obvious relation to the value of the integral. Okay, the only thing that matters is, does the integral converge? If it does, then the series converges. The actual number, I can't tell. At the very beginning of class, what did I write? Someone read it to me. It takes good notes. Yeah, that's it. Read it out loud.
Previously only carried it converges without if we're just not concerned about value.
If converges, we're not concerned about value. Yeah. But some students make a mistake and infer this value as the value of that, and it's not true. It's clearly not true. Right? Unless by some fluke, all of these missing areas, all of them added together would make A1, the first term of the, which is not included here. But by some miracle, that would be true, then the values would be the same. But like, we're not even going to waste 1 second worried about that. We're going to believe what I said at the very beginning of class. Like, for a while, all we're going to care about is, does it convert or diverge? We're not worried about the sum. All right, let's practice. I'm going to say analyze. Summation. N equals 2 to infinity, 1 over n log u. I love this example. We showed on Wednesday that the harmonic series diverges, right? Everyone's good with that. Better be. And the answer I gave for it was like, you know, the terms go to 0, and that's good. In fact, it's necessary, as we showed in the divergence test. But just don't go to 0 fast enough. And so let's say, well, maybe we can fix it. Let's multiply the n. Remember, when the denominator gets bigger, the fractions get smaller. So let's multiply n by something that goes to infinity also, like blow the thing up huge. Now, surely, that's good enough to make it convert. Well, let's find out. The integral was 2 to infinity, 1 over x log x. Take our formula an and convert it to a function of x. Just replace the n's with x. And then we get, of course, this is improper. We know how to deal with that. Limit b goes to infinity. Integral 2b, 1 over x log x. I'm going to rewrite this. That's what I did as like. What I want to do is a u substitution, but I don't want to spell it all out. You know, we could do that if we needed to, but let's let u be ln x. And then what's du? Right there. This is 1 over u to u. Right? U is ln x, du is 1 over x dx. And the antiderivative of 1 over u is ln x. So you get ln of ln 2b. See how that works? Plug in the limits. Ln of ln of b minus ln of ln. I think as b goes to infinity, ln b, what does it do? Goes to infinity, and the log of something that goes to infinity goes to infinity. It goes super, super slow. Amazingly slow. But it goes to infinity. So I get infinity, you know, can this guy fix us? Absolutely not. That's just some number. This guy diverges. terms go to zero, so the divergence test is worthless. But we can integrate it. So I said I love this example because, like I said, we know 1 over n is not good enough. They go to zero, they just don't go fast enough. But then you multiply it by something that is also going to infinity. Let's speed up how fast that thing goes to zero. Still not good enough. Diverges. Are there any questions? All right. I feel like I had a good example in one class. I can't remember. I want to do another. Let's try this one. It's a different one. I think it'll work. Let's pretend like it's not just following our discussion of the integral test. So we moved number 1 way down to the bottom. Is this a geometric series? No, how can you tell? No powers. Yeah. Do the terms go to zero?
Yes.
Yes, they do. No help here. Therefore, the only one left for us is the integral test. Well, let's integrate. 1 to infinity, 1 over x, and x plus 3. Equals. Limit as b goes to infinity. I guess all right. Okay. Anybody know an antiderivative? Or know how to get one? Yes, it's a partial fraction. We need to find constants a and b. So let's do that, and then we'll rewrite. We'll take a little time out from the analyzing the series, and we'll decompose it. Equate numerators. Plug in 0 like we always do, and I get 3a. So a is 1/3. Plug in -3. Get 1 equals -3b. B is -1. Okay, I rattled through that pretty fast. We've done it before. There's nothing very interesting about it. We just crank through it and get our decomposition. So the integral, that actually the limit that I wrote, now modified. 1 to b. And a is plus 1/3. B is minus 1. Okay, everybody with me? Let's factor those 1/3 out. So we're lucky we've got the same constant plus or minus. Just get it out of our way. And we can even take the antiderivative while we're at it. 1/3 limit as b goes to infinity. And I get ln x, right? Everything's positive, no absolute value. So it's minus ln x plus 3. 1 to b. Plug in the B. So I'm going kind of fast. I hope this is all pretty routine. That's safe to say. Any questions for me? Scott can't be here today because of track and field obligations, and he asked me to record it and see him doing it. So it will be posted if you take a slower look at some of these. You can do that. All right, 1/3. Limit is B goes to infinity. Yes, let's deal with the constants. Ln1 is 0, so I get plus Ln4 out here. As B goes to infinity, Ln(b) goes to infinity. Ln(b) plus 3. Yeah, it's just a little bit ahead of Ln(b). We're both checking off to infinity. Infinity minus infinity, we identified in Calc 1 as an indeterminate form, which normally would mean we need to invoke L'Hopital's rule, except logs rescue us. We can use a log property. The difference of logs I can write as the log of the quotient b over b plus 3. Then I have plus Ln4. Everybody follow that? I could have used L'Hopital's rule. I would have to write it as a fraction. And I think the only way to do that is to use log properties. So, but good. As b goes to infinity, what is b over b plus 3 approach? 1. And the log of 1? 0. What's our answer? 1/3 Ln4. The integral converges. What about the series? They behave the same. The integral test says. We do not know the value. It does not, almost certainly, it doesn't converge to 1/3 Ln4. But it does converge by the integral test. Any questions? Just
I think that if it was equal to 0,
if what is equal to 0. If the terms, the divergence test says, if the terms do not go to 0, the series diverges. It does not say if the terms go to 0, it converges. And we know that's not true because the harmonic series diverge. And the very first example I did here, the terms go to 0, in fact, pretty fast. N and log n both are going to infinity, not fast enough. That one diverges. The terms go to 0, it doesn't prove a thing. Like we can just mark the divergence test off the list, but we got to go find another one because it doesn't settle the issue. Okay? You guys studied like symbolic logic in your high school calculus? So, symbolic logic, you run into things like this, which we would read as P implies Q. If P is true, then Q has to be true as well. Okay, and most math theorems are like that. The divergence test says if something happens, then something else is guaranteed to happen, right? The integral test says if the integral converges, the series converges, right? So really common in math. And then it's kind of natural to say, well, let's flip the Q and the P around. But it turns out this is called the converse of that. And whether this is true or not tells us absolutely nothing about the converse. It's a separate logical statement. Okay, and what you're thinking is the converse. Like, well, if the terms don't go to zero, it diverges, and it must be true that if they do go to zero, it converges. But that's the converse. And it's a separate logical statement. In this case, it's false. We've demonstrated it's false by the harmonic as well as by this example right here. When a statement and its converse are always true, that's when we say if and only if. You've heard that language before. And that, it's not just like, I really mean this. It means both of these are true. And then like, that's a really good situation. All right. Any other questions? I was going to say, maybe I shouldn't say this, but all of this work started with this integral. We did some things here. We carried it over here. It's all focused on trying to decide, is that integral converge? We don't care the value. We never, ever will care about the value of the integral. It doesn't tell us anything. So it could be like you're working along and you can say, oh, I can see this is going to converge. Well, then, you might not do this on a test because I might want to see more. But as soon as we know it's going to converge, then like we know the answer. It's going to converge. We don't need the value. The value is meaningless. All right. So the P series. I'm going to call it a test so I can put it on our list of tests. And I suppose it is a test word. It's this series. N equals 1 and going to be 1 over N. If P is less than or equal to 0, one over N of P does not go to 0. So it diverges. By the divergence. For example, if P is -2, well, 1 over N to the -2, that's like N squared. And those go screaming off to infinity, which is not 0. So this is only interesting if P is a positive number. And we've analyzed one P series. Which one? What value of P?
1.
P equals 1, and what did we get? Yeah, and it diverged. But that leaves a lot of others. Any positive number. All right, so let's take a look at the integral test. See what it tells us. Could talk our way through this. We've done on all the others. But because Jesse's answered the geometric question for us twice, but his answer won't work. Is that a geometric series? Twice Jesse said no, because there's no powers. Well, now I have a power. Is it geometric? No, because why?
Because n's not the power.
Correct. Because the power is the same for all the terms. 1 to the P, 2 to the P, 3 to the P. It doesn't change. On a geometric series, the power keeps going up, right? We multiply by r to get from one term to the next. It's not a geometric series. Because I've said that P needs to be positive, the divergence test fails. That makes all the terms go to zero, all for all p's, positive. So the divergence test fails. Guess what? The integral test. It's the one we need to use. So we're going to take a look at the integral from 1 to infinity, 1 over x to the p dx. But maybe that looks familiar. We analyzed that very integral back when we were dealing with improper integrals. And we found out that it converges, and the value doesn't matter, but we did figure it out. Converges to 1 over p minus 1 if p is bigger than 1. Diverges otherwise. And again, we did all this work before, and we had a p in it, and I called it p integrals, I think. Just set us up for today series. You can see what's going to happen. Write 1 over x to the p as x to the minus p. And then to get an antiderivative, you raise the power, divide by the new power. And the question is, does the new power become positive? When you add 1 to it, does it turn from negative? If it does, it diverges. And if it's between 0 and 1, it's in the denominator, so the power is going to be between 0 and minus 1. When you add 1 to it, it becomes positive. No.
So this is different from Sn. Right? If it were Sn, we could just find the limit of that, which would be 0. If we were to analyze Sn.
Well, if we were to analyze Sn, we would need to find a way to write it in a form that we could take the limit of. And that is really, really hard to do unless we have a geometric series or a carefully chosen one. There are 2 of them on the homework. I did one in class. I think only 1, maybe 2. And it has to work out just so that the terms telescope. So you write out S sub n and almost all of the terms go away. That almost never happens. But it happens for a geometric series and it happens for carefully chosen other ones. Okay? And from now on, I mean, we don't have to think about this if we have a geometric series because we've learned everything there is to know about geometry. So this is like our last guy, and even then, I don't think we will ever use it to determine the behavior of the series again, unless I put one like those homework problems on the test in a few weeks. Okay, does that answer your question, Noah? This is actually an if and only if statement and the converse. If it converges, p is bigger than 1. If p is bigger than 1, it converges, both the statement and the converse. Again, the number, not meaningful here. Just the fact that it's finite means the integral converges. So what about this? Summation n equals 1 to infinity, 1 over n squared. Convert it outward. What kind of series is it? It's a p series. What's the value of p? 2. It's 2 bigger than 1. It is. Converges. Here's a fun fact. It's way beyond our ability to prove it. But it actually converges to pi squared over 6. Just about out of time. That's unbelievable. Like, the real numbers, like they're uncountable. Every single point on the number line represents a real number. And somehow the number that tells me about information about circles gets involved here. Like, it's unbelievable. But it's true. What is this? 1/1/4 plus 1/9, 16. Keep going. You get pi squared over 6. Like I said, that's way beyond the ability. What we can say, this is a P series, P equals 2, pick the target. Equals 2, bigger than 1. The P series are pretty easy in the end. Except to remember. Any questions? Have a wonderful weekend. See you Monday.